Okay, good morning, one and all. Today we are going to discuss about the problems on random process through LTI system. You see this problem? If the input is autocorrelation function Rxx of tau is equal to A into e power minus alpha into magnitude of tau, where A and alpha are the constants. Find the output spectral density and draw the output power spectrum for A is given in the spectrum here in the problem itself. A has given the spectrum, that is a SYY of omega is equal to A naught square by 4 into SXX of omega minus omega naught plus SXX of omega plus omega naught. Okay. Now you see here, in the given problem, he has given the autocorrelation function. So the autocorrelation function Fourier transform is SXX of omega. You know this SXX of omega. So Fourier transform of autocorrelation function Rxx of tau is equal to SXX of omega. So you know Fourier transform formula, that is integral minus infinity to plus infinity Rxx of tau into e power minus j omega tau into d tau. Okay, it is the formula of Fourier transform for autocorrelation function. Now, what is the Rxx of tau? That is, we are going to be substitute here. That is A into e power minus alpha into magnitude of tau. So whenever there is a magnitude of tau, that means it takes both positive values as well as negative values. So if you are coming for the limits here, instead of doing, see here, the limits we are substituting negative limits for negative t. So minus infinity to 0 a into e power alpha, this t is a negative. So already there is a minus into minus plus, remaining same. Coming for right side limits, 0 to infinity, a into e power minus alpha into tau. This coming for this here, it is the positive values of tau. So for positive values, tau is positive. For negative values, tau is negative. That's why this e power minus is going to be positive here. This e power minus as it is here. Now if you apply integration for this, you know e power a minus j omega tau d tau integration is just e power a tau d tau integration. So that is as it is, you can write that limits e power a minus j omega tau divided by a minus j omega. Now if you substitute that limits minus infinity to 0, here also e power minus of a plus j omega tau divided by minus of a plus j omega, and if we substitute these limits 0 to infinity, you do it is one already this type of problem already we have done in the classroom also. So that's why you do this problem, you do this calculation. If we substitute these limits minus infinity and 0, anyway here if we substitute instead of tau minus infinity, it is going to be 0, and if we substitute 0, it is going to be 1. So finally we are going to get 1 divided by a minus j omega. Here we are going to get 1 divided by a plus j omega, and you take LCM for this. So a plus j omega plus a minus j omega. So here minus j omega plus j omega gets cancelled. Here a minus j omega into a plus j omega, a square minus b square. So that is a square plus alpha square. Alpha square plus It is not a, it is alpha. Sorry, it is alpha. So finally, if we see the Fourier transform of the given autocorrelation function is Sxx of omega is equal to A into 2 alpha divided by omega square plus alpha square. So in the problem, he has given the power spectral density of output. So Syy of omega means power spectral density of the autocorrelation function in the output side. So A naught square by 4, Sxx of omega minus omega naught. Sxx of omega minus omega naught means it is just whatever the power spectral density of the input signal, input autocorrelation function, that is going to be delayed by omega naught, or omega is going to be replaced with omega minus omega naught. Suppose here Sxx of omega plus omega naught, omega is going to be replaced with omega plus omega naught. So already we obtained the power spectral density. The formula is Sxx of omega is equal to A into 2 alpha divided by omega square plus alpha square. So wherever we have a omega, so in one case, omega is going to be replaced with omega minus omega naught. In another case, omega is replaced with omega plus omega naught. So you see here that formula. Now we have two spectrums. One is a delayed spectrum, another one is a advanced spectrum. Now in the delayed spectrum, Sxx of omega minus omega naught. You observe this original spectrum and this delayed spectrum. What is the difference between these two spectrums here? Wherever you have a omega, that omega is going to be replaced with omega minus omega naught. Wherever you have a omega, that omega is going to be replaced with omega minus omega naught. Similarly, we have omega plus omega naught. So wherever we have a omega, that omega is replaced with omega plus omega. Remaining terms are not going to be changed, because in the problem itself, he has given that output power spectral density is delayed version of the autocorrelation function spectrum or power spectral density of the input and advanced version. So you substitute these two here and you will get the final value Syy of omega. You see here, if you draw this one, so what is this one in time domain? What is the Rxx of tau? What is the Rxx of tau? He has given some A into e power minus alpha into, you see this signal, e power minus alpha into magnitude of tau. So tau takes the both positive values as well as negative values. Whenever tau is increases, that corresponding signal is going to be decreases. Whenever here negative time also tau is increases towards the minus infinity from 0, it is going to be decreases. It is the shape in time domain. It is the shape in time domain. Corresponding spectrum, if you draw the spectrum for this, what is the spectrum we got here? If you see the spectrum, A into 2 alpha divided by omega square plus alpha square. It is your spectrum. It is your spectrum. Now, here, if we substitute different values of omega, both positive values of omega and negative value of omega. Suppose if we substitute for our understanding purpose, if we substitute omega equal to 0, whenever omega equal to 0, 2a into 2 alpha divided by alpha square. So alpha gets cancelled. So you will get 2a by alpha at omega equal to 0. Now that is here he has given. Okay, whenever omega tends to infinity, so it is infinity, so it is going to be 0. That's why at 0, at DC, the amplitude is this one, corresponding magnitude. Whenever omega is goes on increases, that corresponding magnitude is goes on decreases, both positive side of omega as well as negative side of omega. The final value must be 0. It is the power spectral density. If you draw the power spectral density spectrum, for input, but in the output he has given, it is a delayed version as well as advanced version. So the same signal is going to be delayed. Suppose it is 0, it is delayed by omega naught. So this starts here from 0, here it starts at omega naught. No need to do whatever the formulas, all these things. Just delayed version and advanced version. Whatever the amplitude we have, that amplitude we are going to be right. So in the formula, If you see like this, if you have a little bit of confusion, so that's why instead of doing whatever we have a formula, you see this formula. So what is this one? It is delayed signal spectrum. It is advanced spectrum, that corresponding whatever the amplitude we have, that amplitude is going to be multiplied with a naught square by 4. What is the amplitude here? A into 2 alpha. So that is going to be multiplied with this a naught square by 4. So you see here the spectrum, power spectral density, we are going to get two spectrums. One is delayed one, another one is advanced one. Delayed means positive value, advanced means negative value, that corresponding amplitude. So it is the given problem. Autocorrelation function, it is a two-sided signal, and if you draw the power spectral density, or if you find out the power spectral density, and if you draw the magnitude spectrum, the magnitude spectrum is like this. And in the problem itself, we has mentioned that the spectrum, output spectrum, is delayed version, the combination of delayed version and advanced version. So it is going to be represented like this. It is a one problem. And the different types of problems here, we are going to see different how we are going to get the different types of problems in this unit. Now, if you see here, you see the problem. A wide sense stationary random process x of t with power spectral density sxx of omega is applied to the input of a delayed system as shown in figure. Find the power spectral density of output y of t. Again, you see a wide sense stationary random process. It is a random process x of t with power spectral density. Then what is the power spectral density of this x of t? If you find out the autocorrelation function for this, and if you apply Fourier transform for that autocorrelation function, and we are going to get this sxx of omega. You don't confuse here. Is applied to the input of a delayed system. Whatever the system, it is a one original input and another one is delayed. Whatever the signal, whatever the random process, that is going to be delayed by 2t. And what is the output here? X of t minus 2t. And then these two are added and it is equal to y of t. So what is the y of t here? Y of t is equal to x of t plus x of t minus 2t. So that is the given problem. Now you see here, y of t, you observe here, y of t, it is a summation of y of t is summation of x of t plus x of t minus 2t, x of t plus x of t minus 2t. Okay. Okay, na? So y of t is equal to y of t is equal to x of t plus x of t minus 2t. Now, if we apply Fourier transform for this, if we apply the Fourier transform for this, y of omega is equal to x of omega plus what is the Fourier transform of y of t? Y of omega. What is the Fourier transform of x of t? X of omega. What is the Fourier transform of x of t minus 2t? What is the Fourier transform of x of 2 minus tt? You know, according to time shifting property. According to time shifting property, what is the Fourier transform? X of omega into e power minus j omega t naught. In the t naught place, we have a 2t. In the t naught place, we have 2t. So, you replace here. You replace t naught is going to be replaced with 2t. Again, you observe y of t Fourier transform, y of omega, x of t Fourier transform, x of omega, and according to the time shifting property. According to the time shifting property, what is the time shifting property? We know already from the Fourier transform, x of t minus t naught Fourier transform is e power minus j omega t naught into x of omega. So you write as it is x of omega. Instead of t naught, we have a 2t. So e power minus j omega into 2t. Then you take x of omega as a common here. You take the x of omega as a common. So if we take x of omega as common, 1 plus e power minus j omega into e power minus j 2 omega into 2t or omega into 2t, whatever it is. Now, you know what is the transfer function of the system. You have an LTA system. The input is x of t. The input is x of t. Output is a y of t. Fourier transform of x of t is x of omega. Fourier transform of y of t is y of omega. So, what is the y of omega means? Convolution of input and impulse response. So, y of t is equal to x of t convolution with h of t. It is a convolution in time is multiplication in frequency. So, y of omega is equal to h of omega into x of omega. So, finally, h of omega is equal to y of omega by x of omega. It is the, we know the transfer function of the LTI system. H of omega is equal to y of omega by x of omega. It is equal to 1 plus e power minus j 2 omega t. So, it is the transfer function of the given LTE system. So, in the problem, he has asked that what is the output power spectral density? What is the output power spectral density? So, the power spectral density is S by y of omega. We know this formula. It is equal to magnitude of h of omega whole square into sxx of omega. Usually, general LTI system, the input is the x of t, the output is the y of t, the impulse response of the system is h of t. So, what is the y of omega? H of omega into x of omega. But here it is the LTI system is subjected to the random process. Subjected to the random process, we are not applying directly to the random process. We are applying for the autocorrelation function. So, that's why this s by y of omega is equal to magnitude of h of omega whole square into sxx of omega. It is our formula, already we discussed in the class. So, that formula we are just copying here. Now, just now we calculated what is the h of omega. What is the h of omega? 1 plus e power minus j into 2 omega t. So, it is the magnitude. So, magnitude of 1 plus e power minus j 2 omega t whole square into sxx of omega. So, you substitute this one, 1 plus e power minus j omega t. What is the 1 plus e power minus j omega t? If you write this exponential term in terms of cos and sine, what is the e power minus j 2 omega t? Cos 2 omega t minus j sine 2 omega t. And then you separate real terms and imaginary terms. So, what is the real term here? 1 plus cos 2 omega t minus j sine 2 omega t. So, here it is a magnitude. So, whenever there is a magnitude, whenever there is a complex, we are going to write a plus, whenever there is a plus jb into a minus jb. You can write like a plus jb into a minus jb, nothing but x of t complex conjugate of x of t is equal to magnitude of x of t whole square. Similarly, that formula we are going to be right here. We don't confuse here. Suppose we have a signal x of t, a complex conjugate of x of t, complex conjugate of x of t. We are going to be right magnitude of x of t whole square. You can here also we are going to be split like this. One is a original signal, another one is going to be complex conjugate. Suppose it is a original signal, it is the real part, it is the imaginary part. What is the complex conjugate for this? Wherever we have a imaginary term, that is going to be changed into plus. Suppose here it is a plus, it is going to be changed into minus. So that is the formula we are applying here because of this magnitude. Otherwise, directly also we can apply a plus b whole square formula. Then also we can get. So anyway, whether you can do like this or you can apply a plus b whole square, we are going to get this one. So finally, if you, after multiplying, you see this one, it is a minus b into a plus b formula. A minus b, what is the a here? 1 plus cos 2 omega t. What is the b here? J into sine 2 omega. So a square minus b square. So it is a square minus b square, j square is a, it is also minus into minus plus. So sine square 2 omega t sxx of omega. Again, you can abbreviate this one. It is a plus b whole square. A square plus b square plus 2ab and cos square 2 omega, sine square 2 omega, it is going to be get 1. So already there is a 1 plus 1, it is a 2 into 1 plus cos 2 omega t into sxx of omega. So This is going to be right again, cos 2 omega t in terms of cos square function, 2 cos square omega t minus 1. We have a formula. So based on that formula, again you can further simplify. You will get this one. So it is the s by y of omega from the given problem. You see, this type of problem you may expect most of the time because it is not in the syllabus. Usually it is not in the syllabus, but you may expect this question most of the time because the noise topic is not in our syllabus. But you may expect the question most of the time. So you see this question, a random process n of t. What is the n of t here? A noise as a power spectral density g of omega. What is the power spectral density? If you calculate whatever the random process n of t, autocorrelation function for that, and if you apply Fourier transform for that, then whatever the Fourier transform we are going to get, that is going to be called power spectral density of that particular noise. So it is a random process of noise n of t as power spectral density g of omega is equal to n naught by 2 for minus infinity less than omega less than or equal to infinity. It is processed through a LPF means a low pass filter. We know low pass filter transfer function. How it is, it allows only low frequencies and it rejects the high frequencies. Here we are considering the low pass filter means both uh, positive frequencies as well as negative frequencies. So the transfer function h of omega is equal to, he has given the low pass filter transfer function. Transfer function low pass h of omega is equal to 2 minus omega naught less than or equal to omega less than or equal to omega naught. So what is it means? Omega naught, what is the omega naught here? Upper cutoff frequency for both positive side as well as negative side. So in between minus omega naught to plus omega naught, the h of omega is 2 constant and it is 0 otherwise. What does it mean? For up to omega naught, it is going to be allow the signals or whatever it is. After the omega naught, it is not going to be allowed. It is completely attenuated. So that is the given, that is the role of low pass filter. You know about low pass filter. It allows only certain range of frequencies and rejects the other range of frequencies. That is also from 0 to omega naught. Okay. Now, you see here, g of omega he has given n naught by 2. That is for all frequencies. That is for all frequencies. But while coming for this is applied to a low pass filter. If it is applied to a low pass filter, now the output of power spectral density g naught of omega is equal to magnitude of h of omega whole square into g omega. Magnitude of h of, for an LTI system, g naught of output of this random process is equal to magnitude of h of omega whole square into, what is this magnitude of h of omega? Low pass filter characteristics. What is the low pass filter? It allows only from minus omega naught to plus omega naught. Within this range, it is going to be square, and it is going to be multiplied with your power spectral density of noise. Now you see simply this g naught of omega, whatever the within this low range of frequencies, within the range of frequencies, what is your amplitude of the low pass filter? The amplitude of the low pass filter is 2. So it is going to be multiply, it is going to be square 2, that is a square of the 2 is a 4, and it is multiplied with your power spectral density of noise, that is a n naught by 2. Simply multiply, so finally you will get the 2 n naught. So this type of problems also we may expect in this unit. You see the next problem, it is another problem. A random noise x of t having the power spectrum of sxx of omega 3 divided by 49 plus omega square is applied to the network for which h of t is equal to u of t into t square e power minus 2t. The network response is denoted by y of t. A, what is the average power in x of t? B, find the power spectrum of y of t. C, find the average power of y of t. So again you see the random noise. The noise is given here x of t, like x of t, and it has a power spectrum of sxx of omega 3 divided by 49 plus omega square is applied to a network for which h of t impulse response is given u of t into t square e power minus 3t. Similarly, it is also like a similar problem. The network response is denoted by y of t. So, you know what is the uh, power spectrum of input as given? Power spectrum of input is 3 divided by 49 plus omega square. Okay. Next, impulse response you can take here. Now, first one, what is the average power of x of t? So, we don't go for output here. So, just he has asked the average power. You know the formula of power. So, 1 divided by 2 pi within the interval minus infinity to plus infinity sxx of omega into d omega. How it is get? It is nothing but rxx of 0. What is the rxx of 0? What is the rxx of tau? What is the rxx of tau? Inverse Fourier transform of sxx of omega. What is the inverse Fourier transform of sxx of omega? It is equal to 1 divided by 2 pi integral minus infinity to plus infinity sxx of omega into e power j omega tau into d omega. It is our formula. Otherwise, you write here rxx of tau at tau is equal to 0 is equal to pxs. Otherwise, you write in the paper rxx of tau at tau is equal to 0, nothing but pxx, average power. So, what is this rxx of tau? Inverse Fourier transform of sxx of omega. So, you don't confuse here. The pxx means just you find out the inverse Fourier transform of sxx of omega, and then if is nothing but rxx of tau. So, indirectly you can say first you need to find out the rxx of, write the formula for rxx of tau, and then you replace tau with 0. Whenever if you replace tau with 0, e power 0 is going to be 1. So, we will get this formula. We will get this formula. So, 1 divided by 2 pi integral minus infinity to infinity sxx of omega into d omega. You know already he has given the sxx of omega. So, it is going to be right 3 by omega square plus what is the 49? It is a 7 square into d omega. 1 divided by 2 pi integral minus infinity 3 divided by omega square plus 7 square d omega. So, it is a standard formula. It is a standard formula, that is 1 by a tan inverse of omega by a. That formula we know. So, integral minus infinity omega 1 divided by omega square plus a square into d omega. We have a standard formula. So, that formula we are going to write 1 by a. Here a is 7, 1 by a tan inverse of omega by a, omega by 7. And the limits are minus infinity to plus infinity. Tan inverse of infinity is a pi by 2, and tan inverse of minus infinity is a minus pi by 2. So, pi by 2 minus of minus pi by 2 is a pi. So, that is going to be right here pi. Okay. So, finally, the average power of the given noise is 0.2143 watts. Okay. 0.2143 watts. The next one is output power spectrum. You know that formula, output power spectrum. What is the output power spectrum general formula for an LTI system? Syy of omega is equal to magnitude of h of omega whole square into sxx of omega. Syy of omega is equal to magnitude of h of omega whole square into sxx of omega. Okay. So, this Sy of omega is equal to magnitude of h of omega whole square into sxx of omega. So, we need to find out sxx of omega already is given. We need to find out transfer function of the system. In the problem, he has given impulse response. He has given the impulse response. Anyway, the class is going to be stopped within 3 minutes because it is up to 40 minutes only. Hello? Hello?
సార్
ఈ అటెండెన్స్ తీసుకున్నారా
Yes, sir.
ఎవరైనా? అటెండెన్స్ తీసుకున్నారా? మీనాక్షి?
Yes, sir.
అటెండెన్స్ స్క్రీన్ షాట్ తీసారా?
తీస్తున్నాను సార్.
అది మా పాప అంటే ఇంకా ఇది అయిపోద్ది, ఇంక 2 నిమిషాలు కట్ అయిపోద్ది క్లాస్. ఓకే, ఇదిలో డౌట్ ఏమైనా ఉందా? మీనాక్షి మా పాప శ్రీవిద్య,
సార్
ఈ డౌట్ ఏమైనా ఉందా ఇప్పుడు చెప్పిన దాంట్లో?
లేదు సార్.
ఇవి మన అసైన్మెంట్లో కూడా ఇట్లాంటి ప్రాబ్లమ్స్ ఉన్నాయా? ఇప్పుడు అసైన్మెంట్ క్వశ్చన్స్ చెప్పాను.
ఉన్నాయి సార్, ఉన్నాయి సార్, ఉన్నాయి సార్.
అవి చేయండి. ఇది ఒక 2 minutesలో క్లాస్ కట్ అయిపోతుంది. ఇది 40 minutes టైం. ఇది అటెండెన్స్ తీసారా?
తీసాం సార్.
ఓకే, అది 2 minutesలో కట్ అయిపోతుంది. మళ్ళీ మీరేం జాయిన్ అవసరం లేదు, ఎందుకంటే నెక్స్ట్ క్లాస్ మళ్ళీ జాయిన్ అవ్వాలి కాబట్టి. ఓకేనా? ఇది ఎంతవరకు ఉంటుందో అంతవరకు చూడండి. ఓకేనా?
ఓకే సార్.
Okay, you see here, we need to go for calculation of h of omega. So the h of omega is nothing but Fourier transform of h of t. H of omega is nothing but Fourier transform of h of t. So he has given h of t is a t square e power minus 7t into u of t. We know this formula already. In the Laplace transform also we have seen this formula. Whenever there is a t power n e power minus 8 u of t, usually n factorial by s plus a whole power n plus 1. So here what is the n? N is a 2. So here n factorial means 2 factorial divided by, in the Laplace transform usually we are going to write s plus a. In the Fourier transform the s is replaced with j omega. So you remember this formula in Laplace transform, and then you can convert into Fourier transform. Better, my suggestion is, whenever there is this type of problems are there, better you convert into Laplace transform, and then you convert s is equal to j omega. So we know the standard formula for t power n e power at u of t, or t power n e power minus at u of t. So first you see t power n u of t. T power n u of t formula is n factorial by s power n plus 1. Suppose there is a extra e power minus at, s is going to be replaced with s plus a. So here this t power n e power minus 7t u of t is, we just write 2 factorial divided by s plus, what is the s? S is equal to j omega. So j omega plus, here instead of a we are going to get 7. So 7 plus j omega whole